In this video, I want to take a look at some differential equations that are not exact, but we can multiply both sides by some integrating factor and make them exact. Okay. So here we go. We start off with an equation that looks like any other first order differential equation, and we check to see is it exact. And so you take the partial of this with respect to y and the partial of that with respect to x and see if they're equal to each other. If they are, great, it's exact. Then you can do the stuff we've been doing to solve it. If it's not, then let's see if we can make it exact. We're going to find an integrating factor. We're going to look for a function u, which might be a function of x and y, to multiply both sides of this equation by and make it become exact. Okay. So here's what we're going to do. We're going to multiply both sides by u. So this thing here times u. Don't forget to multiply over here by u. Sometimes people forget. So there we go. We want to, what do we want? Yes. If it's going to be exact now, then the partial of this with respect to y has to equal the partial of that with respect to x. So let's take a look at that equation right there. The thing is, this is now a product because m could be a function of x and y, u might be a function of x and y. There's a product rule here, likewise there's a product rule there. So taking the partial derivative of this side with respect to y would be the partial of u with respect to y times m plus u times the partial of m with respect to y. And on this side, taking the partial with respect to x, I get partial of x with respect to n plus u times the partial of u with respect to n plus u times partial of n with respect to x. Okay. Now I'm moving things around a little bit, so I'm getting all the stuff with partials of u on one side and with u on the other side. And then factoring the u out, I get something that looks like this. Now this is beyond us. This is what would be called a first order partial differential equation. This is an equation that involves a function u and its partial derivatives, and we're trying to find that function u. So this is very similar to what we've been doing, but it's a partial differential equation. There's whole courses on partial differential equations, but this is not one of them. We are doing ordinary differential equations. So we can't do this. However, there are some situations where this simplifies into something we can do. Okay. Now, I want to point out that some of your homework questions ask you to verify that this is not exact, and then they give you the multiplier. They give you the function u. Say, okay, multiply both sides, and now check, is it exact? Now solve. Okay. They don't ask you to find it. They just ask you to use it. Because finding it is difficult to do. Finding it means solving this partial differential equation. Now, granted, I'll admit, I never took a partial differential equations class, and I don't even know how to solve it. But I suspect it is actually one that's reasonably easy to solve because this is linear in u and the two partial derivatives of u. So my suspicion is that there is a reasonable way of solving it. In general, but I don't know what it is. I never had an interest in partial differential equations. I never took a course. But let's take a look at a couple of simplifying assumptions and see what happens. So we were looking for the function u to be both a function of x and y. But what if it's just a function of x? All right, let's simplify it down and say, well, maybe we can find something that's just a function of x. Well, if u is just a function of x, then look at this equation here, right, that we ended up with. The partial of u with respect to y would be 0. So that would disappear, and that equation then just becomes, hang on, what's going on here? So then this equation becomes this, which if I solve for u sub x, would be that u sub x equals u times this thing. Okay. Now, this is looking much more like a first order linear or a separable differential equation. The only caveat, the only reason it wouldn't be, is if you still had y's over here. And this was the partial with respect to x. So u is my dependent variable, x is my independent variable. So if there was still y's over here, there would be an issue. But if this is just a function of x, then we can solve this. This is separable or first order linear. You could do it either way. Okay. Likewise, if we assume that u is just a function of y, but not x, then that back up here If u is just a function of y, then the partial of u with respect to x would be 0, and this equation simplifies to this. And again, solving for the partial of u with respect to y here, we get something that looks like this, which again, if this was just a function of y, this would be a separable differential equation or first order linear differential equation in u and y. Okay. Now, one thing I want to point out is notice that in both of them, the numerator here is nx minus ny. This was our check to see whether that was first order linear. No. Check to see if it was exact, right? If it's exact, then those two things are equal to each other, so that numerator would be 0. So under the assumption that u is just a function of x, this equation would be saying, this if it was exact to begin with, and we still tried to find this multiplier, if we assumed u is just a function of x, then this would be saying that the partial of u with respect to x is just 0, which means that u was just a constant. Right? It didn't have any y's in it, and its derivative with respect to x is so the integrating factor would just be a constant, which was like, well, what's the point? Why even bother to multiply? We're already in that situation here. Likewise, down here, if we're assuming this is just a function of y and it was already exact to begin with, then the numerator here would be 0, and we'd be saying the partial with respect to y is 0. Yep. That would be just a constant again. Right. Let's take a look at a couple of examples here. These are a couple of even-numbered problems in the textbook. So this is problem number 18. This first example, I can check to see that it is not exact. Here's the partial with respect to y of this one and the partial with respect to x of that one. They are not equal to each other. Okay, it's not exact. So what I'm going to do is I'm going to look at nx minus ny. The thing is, I'm either going to assume u is a function of x or u is a function of y, and I don't know which one I'm going to do. But notice in both of these cases, the numerator was nx minus ny, the n. Partial with respect to x and minus the partial of n with respect to y. So I'm going to look at that first and then see which one, either divide by n or divide by m, would make more sense. Okay. So where am I? So nx minus ny is this, which actually looks a lot like that one. So if I do... So dividing by n was under the first assumption, right? That was here when I assumed this was just a function of x. So if I take this thing and I divide it by n, I get this 3, actually divide by negative n. This turns out to be 3. And so this differential equation, which is coming from right here, right? This was under the assumption that u is just a function of x. I'm looking at that. So that now becomes just, well, that stuff was just a 3. So the partial of u with respect to x is just 3u. Well, this is exponential growth. This is we've solved this equation many times. This is just u equals some constant times e to the 3x. I don't care. I'm not looking for all the solutions. I just need one. So I'm taking u equals 1. C equals 1 here. And now let's check. If I multiply both sides of the equation by that integrating factor, again, don't forget to multiply over here as well, we can check. Take the partial derivative of this first part with respect to y. Notice this is not a product rule because this is not a function of y out here. This is just with respect to y, this is a constant. So the constant comes along for the ride, then I'm taking the derivative of this stuff inside with respect to y. So 3x squared plus 2x plus 3y squared. And then I'm going to compare that to the partial of this with respect to x. This is a product rule. So I've got the e to the 3x times 2x. That's the first times the second. And then I've got the second times the derivative of the first. And there's a chain rule that pulls that 3 out. And factoring now the e to the 3x out of that, I get 2x plus 3x squared plus 3y squared, which I notice is the same as that. And so sure enough, this is now exact, and I could solve it in the methods that we've shown in the previous video. Okay. One more example. This is problem number 20 out of the textbook. Right. So they give me this 1 plus the quantity x over y minus sine y times y prime is 0. Checking to see if it's exact, take the partial of this with respect to y, which is 0. Take the partial of that with respect to x, which is 1 over y. Those are not equal to each other. Okay? So, so what I'm going to do is I'm going to look at the difference of them, nx minus ny, which is just 1 over y, which, that's just a function of y, and I notice that m over here is just a constant, so it's, you can think of it as just a function of x or just a function of y, because I don't have either variable in it. So comparing that back up here to this assumption, the differential equation I was looking at is the partial v with respect to y times u times this thing divided by m. All right, so this thing divided by m now, where are we? This thing divided by m is just 1 over y, so this differential equation becomes this. And that is definitely separable. I got 1 over u du plus 1 over y dy equals 1 over y dy, sorry. Integrate both sides to get log u equals log y, and u equals y. U equals y. Going back and multiplying, where's my original equation here? This one right here, I'm going to multiply the whole thing by y. So it ends up looking like this, y plus x minus y sine y times y prime equals 0. And now double check. The derivative of this, the partial derivative of this with respect to y is 1. The partial derivative of this with respect to x is 1. It is exact. We could solve it using the methods that we have described in previous videos. Right? There is the process of using an integrating factor to make equations exact.